Hello, thank you very much for coming. I'm Rafael Cabañas from University of Almeria. The work that I'm going to present is about detected changes in the underlying distributions of data stream. Well, we will start by describing the outline of this speech. First, I will explain the motivation of the paper, then I will talk about the background, so we will see some related work, and I will explain what are the hybrid Bayesian networks. Then I will describe how are the models, the methods that we propose. Then we will see an empirical validation, and finally we will see the conclusions of this work. Well, first, let us put into context. We will consider a scenario of learning from data streams. That means that some data is not available, basically because it has not been generated yet. Note that in data streams, there are a time component that is quite important. At each instant of time, we get a set of instances. This set of instances is often called a batch. When learning from data streams, we will learn our model from the data that is available, that is the current batch. But when a new batch has arrived, we will have to update our model. Note that it could happen that the probability that we learn from a batch may differ from the probability that we learn from the following batch. This phenomena may usually happen in data streams, as they usually have non-stationary domains. This is usually known as concept drift. More formally, concept drift can be defined as follows. Here we have this formula where we can see that we have the probability of the set of instances in a particular time step is different from the joining probability in another time step. Similarly, we can define this concept drift if we have labeled data, so we just have to add the class variable here. Let's consider now a very simple toy example where we have a continuous variable y following a Gaussian distribution. So here we plot the value of its mean along time. We can see that it changes. So here is a situation where concept drift happens. This could also happen with discrete variables. Here we have an example. We observe that x1 and x2 change at a certain point while x3 remains almost constant. And actually this is the problem that we face in this paper when we have that only a subset of these states changes while another one remains constant. This will note that this is a very simple example, and here maybe this will not be important, but if we have 70 states, for example, this will be quite problematic. So we will now describe the taxonomy about concept drift. Here, we will categorize concept drift according to the scope. If it affects to the likelihood distribution over the class given the features change, and in this case, we will call it real concept drift, and otherwise, if the prior distribution of the feature drift, we will call it virtual concept drift. Then, we can also make a classification according to the portion of the variable domains that is affected. If the whole domain changes, we will call it full concept drift. On the other hand, if only a subspace of the domain changes, we will call it subconcept drift. And here we can see a comparison between virtual concept drift and virtual subconcept drift. In the full concept drift example, we can see that the probability of each state of x changes. On the other hand, in the subconcept drift example, the probability of the state x3 remains constant. Well, we will describe now some previous work. This paper is clearly based on a previous work about concept drift, the one presented by Borchani at the ITA paper. Moreover, I should mention that one of the co-authors in this paper was also co-author in this work. This paper describes a method for detecting virtual full concept drift using hybrid Bayesian networks. On the other hand, our work can be seen as an extension where we adapt such method for detecting virtual subconcept drift in discrete domains. Now, I think that at this moment, it's important to introduce hybrid Bayesian networks. In particular, we will consider the conditional linear Gaussian model. This is basically a Bayesian network containing discrete and continuous variables. Associated to each discrete node, we will have a conditional probability table, which is often used as a CPT. Then, to continuous node, we have a normal distribution for each discrete parent. In case of continuous parents, we have a linear combination of these continuous parents. Note that in this model, not all combinations between discrete and continuous are allowed. A discrete node will never have a continuous parent. Then, something powerful about this kind of model is the possibility of defining hidden variable, what makes possible the detection of concept drift. A variable of this kind is not associated to any variable in our dataset. Hidden variables will be represented with white nodes, while observed variables will be represented with gray nodes. In this example, the H variable is the hidden variable, and X and Y are the observed variables. In particular, this model is a multivariate Gaussian mixture, which is a model often used. Well, it's actually used for unsupervised clustering. The semantic of the H variable is the following: H summarizes the values of X and Y. Well, here we have the model that was proposed by Borchani, the one for full concept drift detection in continuous data. And here the process that we have to do is the following: we have to build the model with a global H, then we make the inference, and then we analyze the variation of H. Well, note that here we use the so-called Plateau notation, which means that each node inside this rectangle is replicated for each instance or for each time step. It's just a way of simplifying the notation. We see that in this example, for each instance, we have a set. We have the observed variables, and then these observed variables have a hidden variable H, which is parent of those variables. This variable is continuous. And so, when we make inference, what we do is we compute the posterior of each of the hidden variables given the data, that is the observed variables. Finally, the concept drift detection is done by comparing the posterior of H at each time state. If this posterior distribution changes, we will say that concept drift happened. Note that this method only works for continuous variables, because these H variables cannot be parent of any discrete variable. And this will be bad for detecting subconcept drift, basically because this H variable is parent of all the variables, all the feature variables. So, in order to face the first problem, allowing the detection in discrete data, what we will do is a data transformation. Here, with this transformation, we will have an equivalent set of numerical data for each state in the discrete variables. For example, here we have that as x has 3 states, now we have 3 x variables, one associated to each state of the previous variable. And when we have an instance that takes the value x1, this is translated in an instance with 1 for x1 and 0 for the rest. So now, as we have numerical data that will be treated as continuous, we can directly apply the Boltzani model. Note that sometimes for simplicity we will use this notation. We will have joined all the x nodes, but we have written a bold-faced letter. This is just this represents a vector node. This is just for simplifying the notation. Note that we just have to apply data transformation at the very beginning, and then we build the model, and after we infer the posterior of the hidden variables. Note that this model works with discrete data, but may fail with subconcept drift detection. Now, I will explain how we solve the subconcept drift detection. For this, we may split our set of variables into multiple subsets. Here, for example, and each set of variables will have a separate h variable. So the general scheme will be similar. Well, here a variation of the posterior will imply a variation in the states associated to the set. Note that the general procedure is the same, but we make the data transformation, then we build the model, we make the inference, we infer the latent variables given the data, and we just analyze the variation of its posterior distribution. Well, with this model, we will be able to analyze discrete data and also detect, perform the subconcept drift detection. We will finally pass to the empirical validation. Here in this experimentation, we consider 2 data sets. The first one was a synthetic data stream where we modified the sampling distributions. In doing so, we were able to simulate the change of concept. The second one was data from a machine learning contest with about 500,000 of instances. The variables that we analyzed contain 3, 66, and 11 states. The software that we used for implementing this algorithm was the AMIS toolbox, which is an open source library in Java for analyzing data stream with PGNs. Well, if you want more information or you just want to download or test with these tools, you just can visit this link that we saw here. Well, the models that we are going to consider, we have seen 3 models, but obviously we will forget about the Boltzani model that is not possible to analyze because it cannot really treat continuous variables. These are the sampling probabilities for generating the synthetic data. We see that well, at each time step we generated 1,000 of instances, and here we see that some of the probabilities are highlighted. This means that at this instant, at this time step, the probability changes, so we expect to see a change of concept there. And we will consider 2 subsets for making the analysis. The one that is shown in red, the set 1, and then which will allow to analyze changes in the probability of x1 and x3, and then the second set for analyzing the changes in x2, y2, and y3. So this is the model where we have an observed variable, an observed node for its possible state. And then we have a h variable which is parent of x1 and x3, and the other h variable is parent of x2, y2, and y3. Finally, after doing the inference, this is the posterior of the h variables in the model. The red and the blue detects the variation in the sets S1 and S2 respectively. On the other hand, the black line is the full concept detector that aims to detect changes in all the states. If we analyze this plot, we can see that the variation in the sampling probabilities are reflected in the plot. On the other hand, the black line remains almost equal without any variation. So we see that the global or the full concept drift detector does not work with this dataset. The second dataset corresponds with the feature of the packages arriving to a web server. Here we will consider two different contexts. The first one corresponds with the usual traffic, where most of the packages are TCP or HTML. Then the second corresponds with a DOS attack, where most of the packages are ICMP. We will also try to see if some of these peaks that may happen are detected or not. Well, this is the model that we built for the concept drift detection. Here H1 is parent of TCP, ICMP, and HTTP, and this will check the change in the context between the usual traffic and an attack. On the other hand, H2 will detect that if the posterior changes with those probability peaks. And the results were those that we expected. We see that when the red light changes, is in the same moments where there is an attack or the attack ends. On the other hand, the blue line does not change. With this line only correspond to variables that have little changes. And again, the black line that represents the full concept detector does not change. Well, the conclusions of this paper is that we have presented a method for detecting changes in the underlying distributions of discrete streaming data that affect only to some subspace of the variable domain, that is called subconcept drift. We have used hybrid Bayesian networks. We have seen that better results are obtained than with the full concept drift detector. Our method is robust to peaks, and we can deal with large and high-dimensional data. As a future work, well, we will consider to adapt this method or implement this method with probabilistic programming languages. The main reason for that is that this is my current line of research, something quite important. And also we could consider to detect changes in continuous domain that affect only to some subspaces. For example, here we have this part of the distribution remains equal, but this changes with respect to this other graphic. Well, just for I will just end with showing some links. Here, this is the GitHub repository where you can download all the code for reproducing the experiments. Here we have the AMIS Toolbox website, and also you can follow us in the AMIS Toolbox Twitter. Well, thank you very much for your attention, and if you have any question, I will answer them.